Alright, so here is a problem involving the principle of mathematical induction. We want to prove that n factorial is going to be greater than or equal to 2 to the n for all n being in a set of integers where n is greater than or equal to 4. Alright, so it can be useful and it's good practice to say what's going to be our proposition. Our proposition is that n factorial is greater than or equal to 2 to the n for all n that are integers with n greater than or equal to 4. So we look to our basis step. Our basis step is the first case. And in this situation, our first case is when n is equal to 4. Okay? For our basis, 4 factorial is equal to 24, and 2 to the 4th power is equal to 16. So therefore, our first case is true. Next, we have to assume true for n equals k. So we're going to assume true for n equals k. What does that mean for us? Right, we'll just write it down so that we see it, that we have our proposition for our kth case is going to be that k factorial is greater than or equal to 2 to the k for all k in the set of integers where k is greater than or equal to 4. Alright, so we're just going to rewrite it in terms of our kth case, not a specific case. Now, we need to consider when n is equal to k plus 1. Okay, so when n is equal to k plus 1, our left-hand side is equal to k plus 1 factorial. And we're going to work with our left-hand side until we prove that this inequality is going to hold. Right? And that left-hand side we know can be written as k plus 1 times k factorial. Okay. Now, we need to show that this is going to be greater than or equal to the 2 to the k plus 1, which means greater than or equal to 2 times 2 to the k. So that's going to be what we need to show. So we have to think about how can I do that. And with these inequalities, it might involve some manipulation and some creative thinking. Well, we know that k factorial is greater than or equal to 2 to the k. So that means that my left-hand side, right, which is k plus 1 times k factorial, must be greater than or equal to k plus 1 times 2 to the k, and we know that that is true from our kth case, right? That if we look over here, k factorial is greater than or equal to 2 to the k, so this is greater than or equal to this, and we're closer to what we need. We have a 2 to the k here, right? This is what we're trying to show. This is what we need to show. Okay, so what do I know? If k is greater than or equal to 4, k plus 1 is greater than or equal to 2. So what does that mean for us? That means that our left-hand side, which is k plus 1 times k factorial, must be greater than or equal to 2 times 2 to the k, which implies that our p sub k plus 1 is true. All right? That what we have now is, if we're true at our kth case, then k factorial is greater than or equal to 2 to the k. For all k being integers, k greater than or equal to 4. Now, when n equals k plus 1, I have k plus 1 factorial, which is k plus 1 times k factorial. And I need to show that this is going to be greater than 2 to the k plus 1, which means I'm going to be greater than 2 times 2 to the k. All right? From p sub k, I know that k factorial is greater than 2 to the k, so this product must be greater than this product. Also, if k is greater than or equal to 4, I know that k plus 1 must be greater than or equal to 2, so that means that this k plus 1 must be greater than that 2. All right? So, it follows then that my p sub k plus 1 is true whenever my p sub k is true. And my last statement, which we can say is my induction statement, can read in a variety of ways, but we'll shorthand this and say, hey, because p sub n is true for n equals 4, and when p sub k is true, it follows that p sub k plus 1 is also true. By induction, p sub n is true for all n being integers where n is greater than or equal to 4. Okay? Now, for this particular problem, it would be easy to show that if n was 3, this doesn't work, right? 3 factorial, 2 to the third power. No, that's not true when n is equal to 3. But if n is equal to 4, or any value larger than 4, our induction shows that this is always going to have to work. Right? So that's a way that we can work with an induction problem with an inequality. Thank you for your time.